Hello and welcome to lecture 13, which now starts part 3 of the lecture. So we are now looking at data in general and how we can analyze data and how we can relate data to our mathematical models. Of course, the statistical methods we are employing here will also be a kind of mathematical model. So we don't differentiate between, let's say, a pure, for example, dynamical systems-based mathematical model and a statistical model, which we define in this lecture. So, let me go to statistics, therefore, and in general, of course, we cannot do a whole lecture on statistics, but let me just give you a flavor here. And the most important things in statistics are estimators. Then there are confidence, for example, confidence intervals, and then there are tests. We will mainly deal here with estimators because they will also turn up in the treatment of neural networks, which we do at the end of the lecture. Now we have to discuss the general setting of what we do. And that is, of course, done via probability theory. As you know, we have the idea that actually everything we can observe is in the background a stochastic process or has some probability included, which means you can always define a random variable which is producing the data. This can be, for example, even if the process is deterministic, the data still might be stochastic because you have measurement errors. This is the general idea. So what we have is, in general, this random variable x, and the random variable is usually thought to be mapping from a large space, which we call the empirical set or empirical space. And that's where the things you want to observe are happening. So omega needs to be big enough such that it can include all the observations you want to make, potentially at least. But of course, you also have to be careful because omega also will have, if you look at the first lecture we had in this series, you also, of course, have to be careful that omega has well-defined system boundaries. Otherwise, the mathematical modeling and also the statistical models will not be well-defined. Then X is mapping into something we call xi, capital Xi, and this will be the that will contain the numerical values of the observation which you are doing. So in a sense, the random variable x is there in order to translate phenomenon which occur in omega into something you can measure in Xi. So for example, Xi can be measuring the number of events or the things like something being more or less of something or something like that. So typically these will be numbers in Xi. So Xi is a Cartesian product of the conventional mathematical sets. You need to define numbers. Okay, so the probability space, of course, has to be equipped with sigma algebra A, and it has to be equipped with a probability P. And X is of course then mapping into a measure space xi b. That's important. You will need to define this sigma algebra B in the space xi as well, because, for example, you want later to define distributions with the help of integrals, so the Lebesgue integral, and this is all based on measure spaces. So we now denote, of course, you see that we have not defined any probability here, because we want to use the probability defined on the larger space omega, on the probability space omega AP. So we introduce here the induced probability px. So we always write it p to the power x, but that just means it's the induced probability into the space, into the measure space xi b, which is induced by the probability p on the original space omega AP. Formally, you define this as so you take any set in B, which is the space. You look at the origin of that in the space omega. So you take here x to the power -1 of B, and then you can use the probability P on the space omega to define this induced probability Px for all B in B, so for all measurable sets in this space xi. And now we call L of x the distribution of the random variable. This is just given by all the outcomes, so you go through all the sets B in B that that you have, and then you look at the probability, the induced probability of this set B. Yeah, and usually we denote all these probabilities by capital, all these probability distributions by capital L. Okay, now it is important to note that if you have now if you have introduced this random variable x, with the help of that you can now also explain the data. So in general we will denote the data by capital D, and any given single set of data D will be thought to have been created by a single set B in the measure space xi B, and and then we take the random variable x to produce the data. So it's one application of the random variable on on omega, giving you now some outcome in xi, which is also containing the data, the numerical data. Okay, I hope this makes it clear. You can see that this is a very general idea in statistics. Of course, for example, it's now if you know that there are discrete distributions and continuum distributions in this setting, this all depends, of course, on what you have chosen as the space xi. So if xi is a continuum space, for example, a subset of Rk, the real numbers, the k Cartesian product of real numbers, then the distribution, the induced distribution L of x, will be a continuum distribution. But if xi is a discrete space, so for example set the integers to the power k, then this will be also a discrete distribution. Yeah, now we have to come to the idea of a statistical model. So we want to know, so what is the general idea? The general idea is we have, for example, we have a given data set, and now we want to know, we know that, or we assume that this data set has been created via the random variable capital X we discussed in the previous slide. And now, we want to know whether, we want to know something about the distribution of X. So we want to know something about L of X. That was our notation in the previous slide. And of course, we don't know L of X, but we want to infer it from the data. Or we want to later say, what is the best choice for the distribution L of X given the data, for example. So this creates you something that is called a statistical model. And here we look at so-called parametric statistical models. Parametric means that in general we will introduce some parameter or parameters, it can also be several, to this distribution, and then we have, for example, a given set of distributions, but they all will be parametrized by these parameters, and then we are not asked the questions which distributions are the best choice for L of X, but we look at the simpler questions, which parameters do we have to choose inside this given formulation of a probability distribution that best fit the data. So this is the idea of parametric statistics, to introduce these parameters. But I have to say at this stage that, of course, there exists also non-parametric statistics, which thinks it's not actually a good idea to introduce such parameters. And for example, it's better to look at functional approaches. But on the other hand, because later, for example, in neural networks, we also have to introduce parameters. It's the best choice we have in this lecture to have everything based on parametric statistics. So what is a parametric statistical model? Let's go through the definition. So we consider again the measure space Xi B. B is the sigma algebra of the associated to this space Xi, to the numerical space Xi, and omega is our larger empirical set. And now we introduce theta, which is a parameter set, and any theta in this parameter set is then called a parameter. Now we introduce also an induced probability, px, but now this also depends on the parameter theta in theta, capital theta. So this is then becoming a family of induced probability measures on the numerical measure space Xi B. So that means we have now a triple Xi, then the sigma algebra B on Xi, of Xi, and then this induced family of probability measures px theta. And this is a probability space for every theta in the parameter set theta. Now we define some p, which is just defined as the whole family of probability induced probability measure. So this is all p theta x such that theta is in the parameter set. Yeah, then the whole thing we get, this psi BP, is called a parametric statistical model. We have that the distribution of x is then an element in this set P, the family of probability, induced probability measures Px theta. Okay. Now we introduce the so-called maximum likelihood. That is one of the most important ideas in estimation. So we have to discuss it. So again, we look now at this space psi b, and then the family of induced probability measures pi x theta with theta and theta. So this is a statistical model where we assume now we have actually k parameters. So theta is an element in the Borel sets bk. Now we assume that every distribution, induced distribution px theta possesses a density f. And yeah, now given an observation xi in xi, so this is the observation that produces our data, for example. And now we have that then this density of the induced probability px theta is then a mapping, can be interpreted as a mapping from the parameter space to the interval 0 infinity. And this then is called the likelihood function of the observation xi. And then a parameter theta bar is called the maximum likelihood estimation. We often abbreviate that with ML. If you have the condition that f of xi bar theta of xi is the supremum of this density f of xi theta, where you vary the theta in the parameter space capital theta. Now I want to show you that, of course, this definition can be extended to several random variables. This, of course, is necessary in many situations where you have several observations from different, we have to combine different observations from, let's say, for example, different experiments. So we have now n different random variables, x1 up to xn, and they are supposed to be stochastically independent, and they are mapping from probability spaces omega I with sigma algebras AI and probabilities pi to the measure spaces xi I and the sigma algebras bi. Now we have again the parametrized distributions, which are given by L theta of xi, and they all, like before, are supposed to possess densities, which we denote by fi of fi. And then we combine this all together into a big statistical model, which is now given by xi b and these families of induced probability distributions pi theta x, such that theta is in the parameter space. So the parameter space, by the way, you have to see in this generalization as still being the same parameter space with given by capital theta. And now all the spaces here are just the Cartesian products of these single observational spaces xi I. Then the sigma algebras are just direct products of the sigma algebras of each of these measure spaces, and then this family of probability measures is also just the direct product of all the families of induced probability measures, probability distributions of the individual measure spaces. And we vary that, of course, with the parameters theta in capital theta, the parameter set. And then you can interpret this new larger space as a statistical model again, where now the random variable x is having n components, x1 up to xn, and this random variable x is now associated to the likelihood function, which we just call f, and f of omega, the observations, and theta, the parameter. And this is then, of course, just given as the product over all these individual densities fi. Okay, let's discuss logarithm of the densities associated to this larger statistical model. And that is because very often in maximum likelihood theory one actually uses the logarithm, and I want to motivate in a second why. So you define just a new function L of omega theta to be the logarithm of this density of the compound random variable x, which is given by f of omega theta. And this is then just the sum from I equals 1 to n of the logarithm of these individual densities. Now we have that each of the fi's is bigger or equal to 0. This is because they are densities of a probability measure. So this of course is true, and we also have here the logarithm of 0 is minus infinity. And this then of course implies that the set of maxima of this new function L of omega dot is the same as for the original density of this compound random variable x, which is given by f of omega theta. And if the partial derivatives of this f with respect to theta exists, with respect to the parameters exist, then bar theta is a solution of the so-called ML equations, which are given here. So you have here k many equations, as many as you have parameters in the problem, and the ML equations are given by the sum from I equals 1 to n of the partial derivative of the logarithm of the partial derivative of the logarithm of these individual densities with respect to the different parameters, the theta chain. Okay, as I already said, equations 3 are called maximum likelihood equations, abbreviated just by ML. Let's make an example, or give you an example. So what are the ML equations if you assume that the distribution is given by the normal distribution? Okay, so let's consider we have n bigger or equal to 2, and we have in this problem 2 parameters, and that is given by the mean and the variance of the normal distribution. Again, we have then x1 up to xn random variables, and they are all identically distributed with L theta of xi given by the normal distribution. Now the ML equations for the density f of x, oh, that here is a mistake, sorry. So x was not given as the Cartesian product, x was just given as the set of all these n random variables. It was a copying error, apologize. So under theta, which is the two, which theta is given by the two parameters a and sigma to the power 2, which is the mean and variance of the normal distributions. So these are the things you vary in the parameter set capital theta. And if you compute now the ML equations from the previous slide, then you get this result. So you have first to build the partial derivative of f with respect to the mean, and then you have to look at the partial derivative with respect to the variance sigma squared. And if you compute that, then the first condition is that n over n, the dimension, so the number of random variables divided by the variance sigma square times omega bar minus a, this has to be 0. And then in the second condition of the that are derived from the ML equations are that minus n over 2 times 1 over sigma squared plus 1 over 2 sigma to the power 4 times the sum from I equals 1 to n of omega I minus a to the power 2 is also 0. And indeed this system, so these two equations have a unique solution, which is given by bar theta of omega is just a bar of omega and sigma bar to the power 2 of omega. And this is just, if from the previous equation you have that this is omega bar for the first choice of the mean, and for the variance you have 1 over n omega I minus omega bar to the power 2. And this holds under the condition that the variance is positive, but this can indeed be assumed without loss of generality. Okay, so this was the example of the normal distribution when you use maximum likelihood estimation. Now we come to the very important idea of regression. Now this actually will be one of our main things we work towards too in our little excursion into statistics, because we will use regression heavily in order to parameterize our models we have formulated earlier. And we have to understand the basic idea here. So the setting is now again that you have n different random variables. They are real valued. So xi is equal to r. Each xi, sorry, is as the observation space is given by r. And now we assume this form of the random variable. So the random variable is given by a function which is only depending on a parameter theta. So this is xi of theta. And we have here a little error term plus epsilon I. And we assume the same form for each of the n random variables. So please look again at this expression. So now we decompose our random variable into, you can say actually, into a deterministic part which is given by gi of theta, just a function depending on parameters, on the parameter, and then plus some error term epsilon I. So we have theta as a parameter in Rk, so there are excuse me, there are many different such parameters which are unknown, and the functions gi, sorry, this is a mistake, so that should be gi, are then mappings from the parameter space theta into R. And these are somehow given functions. So these are, you can also say they are given functions, they are hypotheses, you know, how you explain the data, which is produced by the random variable xi. Now the errors epsilon I themselves are random variables. They have to be random variables, otherwise xi would be deterministic, because this is a purely deterministic function. So the epsilon I have to be random variables, and they are called errors, and they have to satisfy three conditions. The first one is that you have that the expectation of these random variables is 0. So the error might occur, but it doesn't change the expectation of gi of theta. Now the variance is given by some positive, the variance of these error terms is given by some positive number sigma squared, which is positive and finite. And then also you have that the covariance between two given errors is 0. That means more or less that they are statistically independent errors. So each error, each random variable xi has its own error, which can be statistically independently be investigated from other errors from other random variables. This is exactly what you have here in condition 3. Now I should say a little bit about this. So for example, say you want to create this function gi of theta from some mathematical model, say. So the idea could be, you know, gi, remember, was a mapping from the parameter space theta to R. Now say you have you have a differential equation, say, you know, something like xi d to dt is given by f of xi. Actually this can depend on fx1 up to xn. So these are small xi, which are now, for example, concentrations of a chemical or something. And then you have also the initial condition xi 0 is given by xi of 0. Now the solution of this differential equation here, of course, is also something that that will be parameterized by time. And also, actually, I forgot about that, this differential equation might also have parameters involved. So let's go to here, and let's say we include here parameters theta. In this case, you know, the solution will be some function which we can actually call phi I of theta, which can also be interpreted as a mapping from theta to r. And here, for example, theta would be, of course, also a function of time, because we have here a time derivative, first order differential equation. But that we suppress in this notation. We just make this curve, which is given by phi I, depending on the parameter set theta. And now, of course, you can just set the phi I, the solution of this differential equation. You can just set phi I of theta to be equivalent to gi of theta, and then actually you have converted the regression problem we just discussed before into a parametrization problem of a differential equation. So you will vary then, for example, this computation for each component of the ordinary differential equation, and you try to find you will try to find a solution which depends on the parameters, such that it will best fit, for example, a given data set. So that's one of the reasons why regression is so important for our mathematical modeling lecture. So let's go to least squares. That is, of course, the idea we will have here mostly. So we have that we have these n different random variables, which are these error functions, and let's say each of the errors has also a normal distribution n with a mean 0 and variance sigma squared. Now, and such that these three conditions which I discussed before are all satisfied. And then you can actually compute the density, because that, of course, is given now by the normal distribution. So the density is given then by 2 pi sigma squared to the power minus n over 2 times e to the power minus 1/2, the sum from I equals 1 to n of the difference between xi and gi of theta to the power 2 divided by the variance sigma squared, where theta is in the parameter set theta and sigma squared, the variance, is positive. But it's easy to show that this in turn is equivalent to a minimization problem, where you look at the infimum over the sum from I equals 1 to n of the random variable xi, so the distance distance between xi, the random variable, and the given functions gi of theta, with theta in the parameter set. And here you can see why we call this least squares, because this is a square and you want to minimize the distance of the data produced by the random variable xi and each of these deterministic functions, the given hypotheses, which are imprinted in the functions gi of theta. Now let's discuss the simplest case, where the functions gi are just lines, and then the whole thing is, of course, called linear regression. So you know that a line needs two parameters in order to be well defined or uniquely defined. So we have a two parameter problem with theta 1 and theta 2. And we assume now that we look at linear regression. So we have each of the xi has to be compared with the theta I with theta 1. Sorry, this is a mistake. Just realized this. This has to be a 1. So each of the random variables is measuring a distance from a given line that is given by theta 1 minus theta 2 mi times theta 2. And we have here, of course, also the error function epsilon I. I think there's another mistake here, which is there is one theta here too much. So it's just the line theta 1 plus mi times theta 2. The mi's are, of course, real numbers. So if you have this assumption about a linear form of the functions gi, which is given here, then the ML equations just become a system of n different equations. So this is each of them is the sum from I equals 1 to n of xi minus theta 1 minus theta 2 mi, and that has to be equal to 0. Now you can define the random variable bar x, which is just given as the average over all these random variables. So you sum all of the random variables and divide them by n, and then you have also the average slope of the line, which is given by bar m is equal to the sum over all individual slopes mi divided by n, and you define theta 1 bar as the distance of x bar minus theta 2 m. So bar theta 2 bar m. The minimization then leads to the equation for theta 2, which is given by this expression. And now the line bar x is given by bar theta 1 plus bar theta 2 times bar m is called a regression line. So maybe I explain you for a moment what regression line means, because that was originally introduced by a statistician called Galton, and he had the following measurements. So he introduced length of suns of a certain type of father with a certain body length. So if you look here at the fathers, body length, let's say, it doesn't matter in centimeters. I'm sure Galton was measuring it in inches. And then you have here the suns and the measurements, let's say, in the same with the same units. Then you know you will have that some fathers here will be very small, some other fathers will be a bit taller, will be a bit taller, will be a bit taller, more taller, and so on, and so on. So you want to verify the general trend that a certain father with a certain body length has a son of a certain body length. Of course, you assume you can observe the son over his lifetime, and you look at the final body length when they are grown up. And then the general tendency you will surely observe is that larger fathers will have larger, or taller, sorry, I should say taller. So taller fathers will have taller sons. And you can make, of course there will be some so how I formulated this, so taller fathers have taller sons, this is a linear thinking. So you think the more the father is taller, the more the son is taller, with a certain given a certain length of the two. So we can now try to draw a line which is a least squares line, so it minimizes the distance of these measurement points from the line. And then regression means that this is the general trend embodied by this line, that taller fathers have taller sons. And if you deviate from this line with a certain measurement, then this is interpreted as just some kind of statistical error or variation, which is not too relevant. Of course, that is doubtable. So if the data would not be so neat along the line like I did draw it, but you would, for example, have a data point which is here, then this would be clearly an outlier. It's of course also possible there might, for example, be some genetic interpretation that something did not happen as usual. And then you either classify that as an outlier, or you think actually this statistical law is not good, which assumes that you only have a linear relationship between the length of fathers and sons. Yeah, I hope this explains a little bit the idea of regression. And let's therefore go to a summary. So we have now entered statistics. So we have now officially opened part 3 of the lecture, the final part. And we had a discussion of data. We introduced now statistical models. So far we only had so-called mathematical models, which are mostly interpreted as statistical models, which we had interpreted as graphs and more complex relational structures, or dynamical models, which were then interpreted as stochastic processes and or dynamical systems. But now we have another type of mathematical model, which is the statistical model, which tries to make sense of data. And and this is of course an important part of mathematical model. One of the most important basic estimators for data are the maximum likelihood estimators. So we discussed that. So usually you think certain distributions that are underlying the observation of the data have a certain form, and they can be parametrized. For example, like the normal distribution has been parametrized by its mean and variance, and then the mean and variance can be chosen such that they have maximum likelihood. And then they explain best, given that actually the underlying distribution is really a normal distribution, which of course is an assumption, But then if that assumption is true, in reality, then the maximum likelihood parameters give you the best estimate of the data. And as a simple example, we introduced, or not only a simple but also very important example, we introduced a statistical regression, and especially we are interested in the least squares, which can be used very successfully, in some cases at least, to parameterize mathematical models which have parameters such as stochastic processes, or better in this case ordinary differential equations, or even partial differential equations, for cases where which are completely deterministic. So we discussed, remember, in our statistical regression, so far we have only discussed deterministic models, where in the regression we assumed these deterministic functions gi, and only the error terms were stochastic. Okay, so we will continue with data analysis, and also then in the final lecture we'll also introduce the neural networks, which are much more complicated than these statistical methods, but nevertheless, in order to understand them, we need the basics of statistics, which we have discussed today.